Welcome to e-lectures session for diploma students. Last lecture we have dealt with few problems on series resonance circuits involving a resistor, capacitor and an inductor connected in series with an alternating source. We have derived many definitions and we have derived the expressions for selectivity, bandwidth, quality factor, etc. Based on the discussions what we had in the previous session, we are going to do some problems on series resonant circuits. First of the problem is a series RLC circuit has resistance of 5 ohms, inductance of 10 millihenry and capacitance of 1 microfarad with an applied voltage of 100 volts. So, this 100 volts is nothing but it is a AC source 100 volts variable frequency. Calculate the resonant frequency, circuit current and voltage across the inductor and capacitor. Also find the quality factor. First of all, we should be able to write down all the given data. Here we should ensure whether the circuit is series or parallel. So, the connection is a series circuit, resistance value is 5 ohms, inductance value is 10 millihenry or 10 power minus 3 Henry, capacitance is 1 microfarad or 1 into 10 power minus 6 farad, then voltage is 100 volts. We need to find out the resonance frequency, circuit current, the potential difference across both inductor as well as capacitor, and then finally we need to find out the quality factor. Now let us see. So, this is the expression, that is 1 by 2 pi into square root of LC is the expression for resonance frequency we have derived in the previous session. So, it is a straight away we can substitute the values of the parameters L and C. L and C values are given, right. So, what is the value of L? It is 10 into 10 power minus 3. What is the value of C? It is 1 into 10 power minus 6. Pi value is 3.14. Substituting all the values here, we are getting this expression, and finally upon simplifying this you get 1592 hertz. So, the resonance frequency is equal to 1592 hertz. The meaning is it is the frequency where the value of XL is equal to XC. We have already derived this in the previous session. So, it is inductive, whenever inductive reactance becomes equal to the capacitive reactance, you will get the frequency corresponding to that is called as a resonance frequency. In this case it is 1592 hertz. Then the next step is we need to find out the circuit current. What is the value of circuit? What is the expression to calculate circuit current? It is V by R. So, it is 100 by 5 ohms, which is equal to 20 amperes. The next step is quality factor. We can use any of the formulae which we have discussed. One such formula is 1 by R square root of L by C. So, R is known, which is 5, L is known, which is 10 into 10 power minus 3, then C is known, it is 1 microfarad. Substituting all the values and upon simplifying we get the quality factor value as 20. So, what is the meaning of quality factor? Already we have seen, it is the magnification which happens at the inductance. Suppose if the applied voltage is V, then the magnification will be Q factor into VL. So, this is the magnification which happens across the inductor. Then what is the potential difference across the inductor? It is given by Ohm's law, I into XL, where XL is the inductive reactance, which is nothing but the obstruction given to the flow of current through an inductor. So, XL value is not given straight away. So, we need to find out the value of XL, which is equal to 2 pi f into L, where f is the frequency of the alternating signal. So, I value we have already found out in the previous slide. We have found out its value is 20, then we need to multiply that with 2, then pi is 3.14. What is FR? FR is already calculated, so it is 1592 hertz. Then L value is given, which is 10 into 10 power minus 3. So, we are getting 2000 volts. So, the applied voltage into the Q factor will be your the potential across the inductor. Then what is the potential difference across the capacitor? It is VL is equal to VC, because at FR, at resonance frequency, XL is equal to XC. So, multiplying both sides by I, which is IXL is equal to IXC. So, what is IXL? IXL is nothing but VL, that is the voltage across the inductor. What is IXC? It is nothing but it is the voltage across the capacitor. So, whenever XL becomes equal to XC, then the voltage across the inductor becomes voltage across the capacitor. So, both are 2000 volts. Here you can see the magnification, right. So, what is the applied voltage? Here is the applied voltage is 100. Now, you can see here, now it is been magnified 20 times, or you can straight away find out the potential difference across XL as Q into V. So, what is Q? It is already found out 20. What is V? V is 100. So, it is 2000 volts. So, in this way also you can find out the voltage across the inductor. Similarly, the voltage across the capacitor also you can easily found out by multiplying the selectivity, the Q factor with the applied voltage. So, 20 times the supply voltage has been magnified. Then we will move on to the next example. A series circuit contains a resistance of 4 ohms and an inductance of 0.5 Henry and a variable capacitor across 100 volts 50 hertz supply. Find the capacitance for getting a resonance. Number 2, the potential difference across the inductance and capacitance. Thirdly, you need to find out the Q factor of the series circuit. Now, the given data you need to write down. So, what are the given data? One is the connection is a series connection, resistance is 4 ohms, inductance is 0.5 Henry, voltage is 100 volts, frequency is 50 hertz. We need to find out the capacitance value, then potential difference across L and C, and finally you need to find out the Q factor. Now, so at resonance we know this relation, the inductive reactance will be equal to the capacitive reactance. So, substitute the value of inductive reactance, it is 2 pi FL equal to 1 by 2 pi FC. So, this C value is not known. So, you can bring the C here. So, C is made to move from right hand side to left hand side. Now, you can see 1 by 2 pi F is already there into this 2 pi F will come. So, 2 pi F. So, it is 1 by 4 pi square F square into L, already L is here, right. So, this is the expression for the capacitance value, 1 by 4 pi square F square into L, which is equal to 1 by 4 into 3.14 square into 50 is the frequency of the alternating signal. So, 50 square into what is the value of L? It is 0.5 Henry. So, substituting all those values of F and L and upon simplifying you get the value of C as 20.28 microfarad, because in the beginning of the problem itself it has been given that at resonance what is the value of capacitance. So, we are equating the inductive reactance and capacitive reactance, and then we are finding out the capacitance value from the known values of F and L, that is inductance. Then we need to find out the circuit current. How to find out the circuit current? It is the applied voltage divided by the resistance value. The applied voltage is 100 volts, resistance value is 4 ohms. So, the resultant circuit current is 25 amperes. Then find out the Q factor. So, the parameters R, L and C are known. So, we can straight away find out, we can straight away apply this formula, which is 1 by R square root of L by C. So, by applying this, so this is 0.5 Henry, C value is 20.28 into 10 power minus 6 and R value is 4. So, applying all this parameter values of R, L and C, you can easily find out the value of Q factor, which is 39.25. It means that the voltage across the inductor or the voltage across the capacitor is magnified by 39.25 times the applied voltage, which means that VL is equal to 39.25 into 100. What is the applied voltage here? It is 100. So, it will be 3925 volts across VL. Across the capacitor it is same, which is 3925 volts. So, we are going to find out the potential difference across VL. We can use either of these formulae. One is, you can straight away multiply the circuit current with inductive reactance, or you can apply one more this thing, that is quality factor into applied voltage. Both the formula you can use. So, we can use this formula IXL. What is I? It is 25, already we have found out. Then 2 pi FR into L, 2 3.14. What is the frequency? It is 50 hertz. L is 0.5 Henry. Applying those parameters in the formula, you get 3925. So, you can easily find out the other way of finding out VL is nothing but what is Q? Q is Q into applied voltage, that is V. So, Q is 39.25, we already know that. So, the applied voltage is 100 volts. So, again the same result, 3925 volts. You can use both the formulae. So, what is the potential difference across the capacitor? You do not have to find out IXC, you do not have to multiply Q with the applied voltage. So, it is nothing but it is Vc is equal to VL at resonance. So, straight away we get a value of potential difference across the capacitor as 3925 volts. Then we will move on to the next problem. In a RLC series resonance circuit, a resistance of 10 ohms and an inductance of 20 millihenry are connected in series with a 0.5 microfarad capacitor. Calculate the resonance frequency, Q factor of the coil, half power frequencies. The main difference between this problem and the previous two problems what we did earlier is that in this problem, in addition to the resonance frequency and Q factor, we need to find out the values of half power frequencies also. So, you need to find out bandwidth also you need to find out. Then finally, power consumed at resonance if applied voltage to the circuit is 200 volts AC. We need to find out the power consumed exactly at the resonance frequency. What happens to the power consumed? Now, you write down the given data. The connection is a series connection, resistance value is 10 ohms, inductance is 20 millihenry or 20 into 10 power minus 3 Henry, capacitance value is 0.5 microfarad or 0.5 into 10 power minus 6 farad, applied voltage is 200 volts AC. So, you need to find out resonance frequency, Q factor, bandwidth, half power frequencies, and then finally, you need to find out the power consumed at resonance. Now, resonance frequency formula is 1 by 2 pi into square root of LC. So, we know the values of L and C. L is equal to 20 millihenry. So, or 20 into 10 power minus 3 Henry. C is equal to 0.5 microfarad. So, we are going to substitute these two values in the formula, and after simplifying you get 1592 hertz. Then you need to find out the quality factor. So, the quality factor formula is 1 by R square root of L by C. For L you substitute 20 millihenry, and for the capacitance value you substitute 0.5 microfarad and simplify. Finally, you get Q is equal to 20. There is no unit for the quality factor. Then how to find out the half power frequencies? Here is the lower cutoff frequency or lower half power frequency F1. Formula is Fr minus R by 4 pi L, where Fr is the resonance frequency, R is the resistance, and L is the inductance of the circuit. So, Fr is equal to 1592 minus 10 by 4 pi into 20 into 10 power minus 3. So, after simplification you get the lower half power frequency as 1552. Then how to find out the upper cutoff frequency? So, upper cutoff frequency is Fr plus R by 4 pi L. So, applying the values of resonance frequency and the resistance and inductance values, we get the upper cutoff frequency as 1632. Now, if you could recall the pictorial representation of frequency versus current. So, this is your current. So, this is the maximum current. So, this is I max. I max occurs exactly at a frequency called as resonance frequency. Fr is the resonance frequency. Then how to find out the lower and upper cutoff frequency? This is the I max, right. Exactly at resonance current will be maximum, because their impedance becomes equal to R. Due to the cancellation of XL and XC, the impedance becomes Z equal to R, which is minimum. So, whenever the impedance becomes very minimum, the current will be the maximum. Now, you take 70.7 percentage of I max. So, it will be coming over here. So, 0.707 I max if you take and draw a straight line like this. So, the straight line will cut the inverted U curve under on two parts, right. One is the lower cutoff frequency F1. So, this is the upper cutoff frequency F2. Now, after finding out the lower cutoff frequency and upper cutoff frequency, you can ensure that the lower cutoff frequency is much lesser than the resonance frequency. Now, you can check the resonance frequency is 1592, whereas the lower cutoff frequency is 1552. So, it is much less than this value, then it is correct. Then what is the upper cutoff frequency? So, the upper cutoff frequency is 1632. So, this is 1632. So, this is 1552. So, what is Fr? It is 1592. So, it is exactly midway between the lower cutoff frequency and the upper cutoff frequency. So, hence fourth it is correct. Then we need to find out the bandwidth. How to find out the bandwidth? Once you find out the values of lower cutoff frequency and upper cutoff frequency, then you find out the difference between the upper cutoff frequency and the lower cutoff frequency. So, the two half power frequencies already it has been found out. So, subtract the lower half power frequency from the upper half power frequency, which is 1632 minus 1552, which is 80 hertz. So, either side of this frequency you have the lower half power frequency and upper half power frequency at a distance of 40 hertz on each side. So, that is the meaning. The entire band is 80. So, 40 this way and 40 this way. So, this is Fr. So, when you subtract 40 from Fr, you will get lower half power frequency. When you add 40 with Fr, you will get the upper cutoff frequency F2. So, that is the meaning. So, what is power? Power is equal to V into I into cos theta. So, V is the applied voltage that is the alternating voltage being applied, I is the current, that is the total current, cos theta is the power factor. Now, V is the applied voltage which is 200. How to calculate I? I is equal to basically V by Z, but we are substituting V by R. Why we are substituting V by R? Already we have learned this. So, exactly at resonance Z becomes R, because this J plus XL minus XC, this term will no longer appear. So, this term will no longer appear because XL is equal to XC. So, XL minus XC becomes 0. So, the impedance becomes a pure resistive circuit. So, that is the reason why we are calculating, instead of V by Z we are calculating V by R. So, what is V? It is 200, R has a value 10, then what is cos theta? How cos theta has become 1? So, at resonance what happens? It is a purely resistive network. In a purely resistive network we have already seen, if this is the phasor of voltage, so where should I plot the current phasor? Since phi, that is phi is equal to 0, only when phi is equal to 0, then cos phi will be 1. Since cos theta is 1, it indirectly implies that theta value is 0. If theta value is 0, there is no phase angle difference between voltage and current. So, I should plot the current on the same axis, that of your voltage. There is no phase angle. Suppose if this is, there is no phase angle difference. If this is the reference point x, whenever you rotate, this is the center point of the phasor with O as a center. If you rotate the phasor in the anti-clockwise direction, then both V as well as I will reach the reference point at the same instant of time. So, it means that there is no phase lag between V and I due to the presence of a resistive network. Suppose if the network is having both resistance and inductance, definitely the phasor would be like this. So, this is V. If there is an inductance, so there is a phase angle like this. So, this is theta. So, this is I. So, the I will be lagging behind the voltage by a few angle. If it is a pure inductance, then you have, this is V, then I will be exactly 90 degrees lagging the voltage if it is a pure inductor. So, why the current is lagging behind the voltage by a small angle which is less than 90? Due to the presence of R plus XL here. Suppose if there is a presence of R and XC, then you will have voltage like this, then you will have a current. This is the total current. What I am talking about is the total current. So, this is your theta. So, this is the presence of R plus XC. So, the current will be leading the voltage. While drawing the phasor diagram, you ensure that the voltage phasor is greater than the current phasor, because current is equal to voltage by impedance. So, when compared to the magnitude of voltage, the current value will be much lesser. That is the reason why the voltage phasor is greater, the current phasor is shown as a small value. Then, so here why it is made 1? Because of the presence of a pure resistive network. Then 200 into 20 into 1, you have the power consumed at resonant frequency P is equal to 4000 watts. Now, the answer is resonance frequency is 1592 hertz, half power frequencies, that is F1 is the lower half power frequency, which is equal to 1552 hertz, and the upper half power frequency is 1632 hertz. Then power is equal to 4000 hertz, Q factor is equal to 20, bandwidth is equal to 80. Suppose if you are asked to find out the voltage across the inductance and the voltage across the capacitance, straight away you can find out VL is equal to Q into V. So, what is Q? 20. What is V? V is 200, which is applied voltage. So, once you multiply this, you will get 4000 volts. So, this is the voltage magnification occurs during the resonance value. Now, we will move on to the parallel resonance. So far we have discussed something about the series resonance circuits involving resistance, inductance and capacitance. We have derived expressions for various parameters such as selectivity, then bandwidth, Q factor, resonance frequency, lower half power frequency, upper half power frequency, etc., etc. Then we have dealt with the magnification issues also, how the voltage is getting, applied voltage is getting magnified during resonance, etc., in a series circuit. While the passive elements R, L and C are connected in series, we need to find out all these things. We have done that also. In parallel resonance, what happens? The resistance and the capacitance and the inductance all are connected in parallel fashion to the applied voltage. Now, we are going to deal with the parallel resonance. Consider as RLC circuit in which resistor, inductor and capacitor are connected in parallel to each other. This parallel combination is supplied by voltage a voltage. In parallel resonance circuit, the voltage across each element remains the same and the current gets divided in each component depending on the impedance of each component. The total current is drawn from the supply is equal to the vectorial sum of the resistive, inductive and capacitive current. So, we will have a quick recap of whatever we have learned today. So, we have done problems on series resonance circuits involving quality factor, bandwidth, lower half power frequencies, higher half power frequency, resonant frequency, etc. Thank you.